aware, like, where some of this math that you're actually learning in future years of math and physics could be done. All right, so I'm on page 172. You with me on this adventure? I think it's like 168 if you have the packet. Okay. All right, so this says, use the function h at t equals negative 16t squared plus vt plus s. Okay, like, dude, let's just kind of look at this and survive with this a little bit. All right, so that's the equation they give you. And if it seems like ants are walking around a screen or on your paper when you're looking at that, it's okay. But let's kind of slowly decipher a few things. Okay? This means we're looking at some sort of height. Okay? H at t is the same thing as writing y equals. Is that okay so far? And again, I'm just trying to baby step this a little bit. I want us just to kind of have a somewhat of a understanding of these things are actually used. Okay? This is the height of an upward projectile after t seconds. So our t is time in seconds. So I want you to think about this. If you were to take an object and throw it up in the air, it could be in the air for a couple of seconds. Do you agree?
Yeah.
Eventually, it'll probably hit the ground. Agree? That make sense? All right. So that's kind of what we need to start thinking about. This v is called the initial velocity. And you're like, what's this velocity you speak of? It's the speed of something. If I took a ball, so I took this tennis ball right here, and I threw it up into the air, my arm and my hand are going to exert a certain amount of speed on the ball that when it releases from my hand, that speed, right as it leaves my hand, is that speed. Does that make sense? So that's what velocity is. So like if I threw something, let's say I threw a ball up and it's going to go travel at 5 feet per second. That means it's going 5 feet each second. Now, of course, it's going to change speed because the forces that are acting upon that ball as the ball is flying through the air is coefficient of friction of air, which you don't necessarily need to know, and the force of gravity, which is the earth pulling it back down. Okay? Now, this S value is kind of goofy. What you got? Oh, okay. So this S value is the initial height. Okay, now, again, my friends, I'm not going to have you work on this type of problem on the quiz or the test. We're not going to worry about it. But I wanted this to be a presentation of kind of, hey, what do we have? I mean, this is a tough concept, but mathematically, I think you have the math that you could actually do some stuff with it. So we have everything that is basically there. So now, for problem number 3, it says, a rocket is launched from an 80-foot tower. Okay, so think about this. We have like a tower. Okay, we have a tower, and we have this rocket that we're launching from the tower. This would be the flames coming out because it's launching. Okay, so does that make sense? So basically, with all hopes, we hope that this rocket would travel upward and then start coming downward. So do you agree that that could be a thing? So we're on top of this 80-foot tall tower. Okay, this rocket is launching off the top of this tall tower. Like 80 feet is like 8 stories. Like picture a building that has 8 floors to it. That's basically an 80-foot tower. You know, it might be a little bit off, but for the most part, that's kind of something to visualize. All right, they tell us that it has an initial velocity of 212 feet per second. Okay, and this is feet. Okay? Okay, so we have enough information to start filling out our equation. So the negative 16 t squared plus 212 t plus 80. This is my height equation. Okay, now I would probably be really safe to say that if we were to plug that into the quadratic formula, it's going to be pretty ugly. I mean, this is, you better have a calculator to do this kind of math. And don't worry, again, I'm not going to have you do this on the test or quiz, but I just want you to see that this is something that's taking place. So does everyone understand the thing? We have a tall tower, 80 feet tall. There's a rocket on top of it. We launch the rocket. The rocket launches going 212 feet per second up into the air. That rocket follows a parabolic arc and then comes back down. Okay? That's what's taking place. So some things that we might think about this. This parabola is going to have a y-intercept at 80, and it's going to do this. And this is basically like the ground. Okay? So that's what this problem's conveying. Why does the y-intercept at 80? Well, it started 80 feet up off the ground. Okay? The ground is below where it's actually launching. So it's going to launch up, follow like a curve, and then come back down and smash into the planet. Okay? That's what's taking place. So it's the first thing it says, we want to find the maximum height. So I bet you could answer this question. What would this point right here be called as far as a parabola goes? What is this top red point going to be called as far as the parabola goes? Vertex. Okay? So if that's called the vertex, then I can come and label a few things. I know that my A value is negative 16, my B value is 212, and my C value is 80. Okay? And I bet you that's stuff that you could easily tell me. Agree? Like, you can be like, dude, vertex is either the highest point or the lowest point on a parabola. It's a turning point. Cool. It goes from a squared to a non-squared to just a number. That's A, B's, and C's all day long. So what was, back when we first started parabolas, what was the first thing we did to find like the x value of the vertex or the axis of symmetry? What equation was it? Anyone recall? What was the original equation that we did to find the x value of the vertex? It was negative. Anybody? B over. Do you remember seeing this? 2a. Do you remember seeing that?
Yes.
And then, whatever that was, we plug back into the original function to get the y value. And then we do the pi. We plug in, right? So again, we have enough information to do this, so I'm going to go negative 212 over 2 times negative 16, comma, and we still have to plug it in. Now, this is where you're going to jump on using a calculator. So you're going to go just doing the math. This actually comes out to 6.625. Okay? So let's reference what that 6.625 means. This is seconds. So at 6.625 seconds after this rocket has been launched off the top of an 80-foot building, it got to its highest point. So think about what, if you were to launch a rocket, this is basically how long 6.625 seconds would be. Ready? And go. rocket's at the max. Does it seem like it's kind of up for a little longer amount of time?
Yeah.
I mean, kind of. I mean, if you're launching a people up into outer space, it's going to be a lot more than 6.6 seconds because you don't want the rocket to come crashing back down into Earth. Okay, so what I want to do is, what do you think I should do with the 6.625 in relation to these t values here? Plug it in. And again, this is kind of nasty looking. And again, this is something that you would definitely want to have a calculator available, because there's an awful lot of math that's taken place. And I know that some of you get really hung up on stuff. You're like, oh, and you're like, dude, just type in the numbers. How do you know what numbers? What numbers do we have there? Okay, so again, I'm using the calculator to do this stuff. Times 6.625 quantity squared plus 212 times 6.625 plus 80. So this, if I do this, all of this math, it gets me 782.25. So this is right here. This is my max height. So does this seem like this might be kind of a fun rocket to watch? It's on top of an 80-foot building. It launches. It flies for 6.625 seconds and gets to 782.25 feet above the ground. Okay, that's kind of high up there. I definitely don't think anyone could throw a ball that high, but I think a rocket could do that. I mean, that's not going to get it out of orbit. It's under 1,000 feet. But that's basically what's taking place with this problem. Okay? So this answers our problem with our vertex. But then it says, hey, you know what? After 3 seconds, how high is this up? Now, let's use a little thought process here. Okay, just some critical thinking. How long does it take before it gets to its maximum height? How long does this rocket take to get to its maximum height? 6.625 seconds, right? So if I want to know how high the rocket is after 3 seconds, has it gotten to its maximum height yet? No. So would you feel comfortable that at 3 seconds, I have to have a number smaller than 782.25 feet? Does that make sense? Okay. So friends, what do you think I should do with that 3 seconds? Plug it in for time again. Okay, so I got negative 16, 3 squared, plus 212 times 3, plus 80. So if I do this, this is going to tell me how high the rocket is after 3 seconds. So the rocket after 3 seconds is 572 feet up in the air. Is 572 feet a smaller number than 782.25 feet? Yeah. Does that make sense? If you take 6.6 to get up to the 782, what do you think it makes sense for 3 seconds to get up to 572? I think so. I mean, physics doesn't lie. And we can't do physics without math. So I don't know, kind of cool. And then it says, hey, when's this rocket going to hit the ground? You know what I'm going to do? We're actually going to look at a visual representation. I'm going to use something called Desmos. No, you can't use Desmos yet. But Desmos is a free operator. You don't need that. But I'm going to plug in my equation. I know I got... Somebody tell me what my original equation is. Y equals negative 16. It's t squared, but I'm going to use x squared. Is that okay? Plus, what was my initial velocity? 212x. And then my initial height was 80, right? All right. So I'm going to zoom out. So that's part of my parabola going up. Oh, there's my other part coming down. Okay. So I can kind of squish this down and say, I mean, here's the neat thing that Desmos could do with you. This is my parabola. I got to find the top of it somewhere up here. Can you see the parabola? So Desmos will do this. What did we say my vertex was? Is it that? Oh, darn, Desmos did it that quickly. Actually, I can bring this in a little bit. All right, so now this red is the path of our rocket. This is what our rocket did. It went up, and then it came down. Okay? So here's a couple things to know. Let's go home. If I click right here, so at 13.617 seconds after I have launched my rocket off this 80-foot tall building with an initial velocity of 212 feet per second going upwards, at 13.617 seconds, this rocket comes smashing back down onto the planet. Hopefully it doesn't hit your friend.
Oh no.
If it does, point and laugh.
Okay.
And they maybe call 911. I launched a rocket. My friend tried to catch it. Oops.
Is your friend breathing?
Reuben.
What?
Reuben. All right. So I just wanted to show you some perspective on this type of problem. I mean, yeah, I could have used the quadratic formula on this to find that same value, but it's nicer when you take a look at it. So let's move to number 4. So number 4 is we're punting a football, but we're still using this equation. And it says here, a football is punted with an initial velocity of 51 feet per second. So somebody kicked a ball. Okay? They said, so you have this person who's standing here. This is this guy's leg, and here is his kicking leg. And here is the football. Let's pretend Stirrup can draw. So they told us that this guy's leg was actually 4 feet off the ground when he kicked it. Well, that's my S value. So we're going to plug all this back in. 16t squared plus 51t plus 4. And says, what's the maximum height of the football and when does it hit the ground? Well, dude, again, I think Desmos is kind of fun to play with. So I get y equals negative 16x squared plus 51x plus 4. Okay. So this guy has got one heck of a foot. Is my equation the same as what I just wrote down? So if I click on this, at roughly 1.6 seconds after I have just kicked the football, that football is now 44.6 feet up off the ground. So it says, what would the maximum height of the ball be? 44.6 feet above the ground. What is, when will this ball come back and hit the ground? Find where it crosses the x-axis. At 3.264 seconds after this person kicked the ball, it's going to hit the ground. I mean, that's the long and the short of this kind of stuff. Okay? All right. My friends, that kind of takes care of it. Granted, I'm not going to give you that on a test, but I just wanted you to have a little more visual of kind of what's taking place. I mean, I know a lot of times you see like 3 words streamed together in a row, and if it didn't come on a Snapchat, Instagram, TikTok, Paddywhack, Give the Dog a Bone, whatever social media you're using, You're not interested in it, especially if it's math. Okay, I get it. But this is how it works.
Also, did you know Pixar also uses this? So if you ever work for Pixar or for Disney, when you develop the cartoons or anything like that, you actually do use math. You do use Desmos. I think they use some sort of Desmos because, like, I think they have to use a specific equation for like Murda's hair because it's curly and it was never developed technology-wise. So when they developed Brave, they had to develop a whole new equation to actually have the curls in her hair. So
Kind of
if
cool.
you ever work for Pixar,
There you go.
pretty cool.
What up?
For this one,
It's math
do you have
that
to
you
leave
don't.
that in the
So
room?
what's negative? Yeah, stay under there. Keep 9 minus 32 is
As?
Whereas
Like keep it?
9 minus 32
Oh,
is
do it?
negative 23. So leave negative 23 under the root.
Okay.
All right.
Oh, I divided. Wait, no, that doesn't make sense.
You drive. You drive. You have to.
Oh, you said
when
you
you drive,
27?
you're using that. Because even though you're not like saying, oh, the distance between this car and this car is this feet, you're still estimating the distance. Right? When you go buy something, you have to use money, right?
I mean, actually, I get, if that's,
But here's the
I
thing,
get,
do you
I
check?
get cash
But
for my
here's the thing,
job.
do you check, right, do you check out prices to see if there's a discount on food? Even when you use a card?
Oh, yeah.
That's
Well,
crazy.
you don't really do it as much now because you are using mom and dad's money, right?
I actually have my own.
You got your own?
job, and I
Okay. Good for you.
So I just like to use
But
my
also too, you're also like talking about the rate of your job, right? Like you have to make sure you're getting paid for your value.
Exactly.
Yeah, if you work 31 hours and you're getting paid $15.75 an hour, don't you want to make sure that they paid you the right amount? Oh yeah. All right. Hey friends, I'm on page 173. If you have the packet, it's probably like 169, 170. This says worksheet number 16. And these types of problems you actually might see on the test on Tuesday. It says the area of a rectangle is 48 square meters. Area of a rectangle. So the area is length times width. Agree? All right, so I'm going to draw myself a rectangle because I need something to look at. So I'm going to call this length. I'm going to call this width. And I know that area is length times width because I learned that when I was like 26. But they tell us that the area is equal to 48 square meters, right? Square meters, m squared. That doesn't mean that it's a quadratic. We're just talking about meters. So that means that 48 is equal to length times width. Agree? All right, let's see what else this problem tells us. It says if the length is equal to 3 times the width, what are the dimensions of the rectangle? Okay, so I was able to create another little equation here. So notice I have this equation here, and I have this equation too here. This is representation. Okay, so would you feel comfortable if I were to take 3W, still with me, and plug it in here for L? Could I do that? Which means 3W times W equals 48. And W times W is W squared. Divide by 3, divide by 3. 48 divided by 3 this week is? What do you think? How many times 3 going to 48? 16. All right. Now, we're going to go root, and when we go root, we don't forget the plus minus, so I get W equals plus or minus 4. Now, here's the problem. Can I measure something as a negative distance? No. It's like, hey, how far did you walk today? Negative 3 feet. What? No, you walked 3 feet. I mean, hopefully you walk more than that. But, so I'm only going to use the positive component, so I'm using 4. What is 4? Which letter is 4? width. So this is 4 meters. And we know that length is 3 times 4, and 3 times 4 is? So my rectangle is 12 meters long and 4 meters wide. Okay? And if I go 12 times 4, I get 48.
Why did you get 3W?
Well, they told us on the second sentence, if the length is 3 times the width, so L equals 3W. That cool? All right, friends. Does that somewhat make sense? So item 1 I would do on these problems is I would probably draw the shape that they have, identify what you know about the shape, length, width, things like that, and then go from that. I mean, I'm pretty sure we've all been introduced to area of a rectangle and perimeter of a rectangle. I'm pretty sure you've seen that at least 4 times in 4 different grades. All right, let's go to problem number 2. Problem number 2. It says the perimeter of a rectangle. So what should I do first? Let's draw ourselves a little picture. I have length, I have width. Agree? So the perimeter of a rectangle is 20 centimeters, and the area is 24. So I know that the perimeter equation is 2L plus 2W, and I know the area equation is length times width. Okay? But now they told us that the perimeter is 20, so we get this. Okay? And they told us the area is 24. Okay? Find the dimensions of the rectangle. Okay, so let's take a look at this first. What do you think I could divide everything by? What do you think I could divide everything by? 2. Divide by 2, divide by 2, divide by 2. So that gives me 10 equals L plus W. You with me so far? Okay. Now, I'm going to go to this equation. Get that equation there. So, if I were to modify this, let's see. Nick, should I have L equals or W equals? Your choice. L equals. So Nick chose L, so I'm going to subtract W from both sides here. So I'm going to get L equals 10 minus W. Okay? So I modified that top equation. So 10 minus W. What do you think I can do with that 10 minus W with my other equation? What can I do here and here with it? Can I replace the L on 24 equals L times W? Can I replace that L with 10 minus W, you think? Yeah, let's go for it. So I get 24. My L, it was L. Now I'm going to plug 10 minus W in. And my W just stays W. Okay, we can't really solve it like this, but I'm going to distribute here. I could do that. I can move this over by adding W squared, minus 10W, minus 10W. So let's see what this comes out to. W squared minus 10W plus 24 equals 0. Should we go right to the quadratic, or do you think we could maybe factor it? I get a positive 24, agree? In order to get a positive 24, if that's a negative, I know both signs are negative, agree? I know that 1 times 24 is 24. I know that 2 times 12 is 24. I know that 3 times 8 is 24. And I know that 4 times 6 is 24. Which set of those numbers, or those factors, would add up to negative 10 if they are both negative? Eight and 3? No. That makes negative 11. 2 and 12 would if one was positive and one's negative. But, so this won't work because they both have to be negative. So that gives me negative 14. But if these signs were plus minus, that 2 and 12 all day long works. Okay? But in this case, I have to go negative 4x minus 6x. That gives me the negative 10, or w in this case. So let's replace it. Oops. Minus 4w minus 6w plus 24. Extend my page. Looks like I have a w in common here. That leaves me w minus 4. Take out a negative 6, w minus 4. So I get an answer of w minus 6 and w minus 4. So w is equal to 6 and 4. Are those both positive numbers? Okay. In fact, the 4 and 6, this is 4, this is 6. Is 4 times 6 24? Yeah. Is 4 plus 4, which is 8, and 6 plus 6, which is 12, add up to 20? Yeah. There's my answers. All right. So what I would like you to do, we will mark this off on Monday. I'm going to do two things for you. I would like you to do page 173, try number 3 and 4. I'm also going to give you your take-home test. Okay? Take-home test. I will post the video on Monday. But I would strongly encourage, I think some of you, I know a great deal of you watch the video, and that's fantastic. I applaud you. But I think a great deal of you turn the video on with nothing tried on your take-home test, and you copy down everything I write, and then when you get to the test, you're like, I don't understand this. You didn't practice. Well, I have everything on my take-home test. That's everything that I wrote. Where's your practice? Oh, I just copied down what you said. You didn't practice it. So I'm giving you the take-home test early so you can get a start on it, get a practice on it, and then on Monday maybe watch the video. That would get you along. Okay?
The biggest suggestion that I would do for the take-home test is try it out, assess it.